Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue forward with our sum and difference identities for the trigonometric functions. You should have already watched all the videos in the series up to this point. Now we're going to use those identities really in what I think are the most entertaining ways, which is proofs. And we'll start with a proof of a formula that we've taken for granted this entire time. And I tell my students, and I've said it in the video, previous video, that the cofunction identities, which is this is one of them, cosine of pi over 2 minus theta is sine of theta, those cannot be proven until you have better trigonometric technology. And here we are, we have that better trig technology. Let's go ahead and prove this theorem. So we know that the cosine of pi over 2 minus theta can be rewritten because that's a difference of angles. And that difference of angles formula for the cosine is the cosine of the first angle times the cosine of the second angle. And then if that's a minus, we'll have a plus here. This cosine doesn't like its SIGN sign. It doesn't like its sign. So if it's a minus inside the argument, it'll be a plus, an addition outside. So we have cosine of pi over 2 times cosine of theta plus sine of pi over 2 sine of theta. And now we just evaluate these. Cosine of pi over 2. I actually, oddly enough, and I don't know why I do this, but I don't spend enough time talking about the quadrantal angles in trigonometry. So let me spend a moment here just to remind you, whenever you have an angle like this that lands on an axis, it's much easier to go ahead and graph out that cosine curve and find out, look at that cosine curve to find out what the value is at pi over 2. Notice the value of the cosine at pi over 2 is 0. That's its height, its y value. So the cosine of pi over 2, that's just 0 times the cosine of theta, but that doesn't actually matter because 0 times anything is 0. Sine of pi over 2, same thing. Pi over 2 is a quadrantal angle. So I'm just going to quickly sketch out the sine curve. It goes for 2 pi, that's the regular period. Halfway through is pi, and half of that is pi over 2. The sine of pi over 2, what's the y value when you plug in pi over 2? Oh, it's a y value of 1. So the sine of pi over 2 must be a 1. So this is plus 1 sine of theta. And simplifying this down, 0 plus 1 sine theta is just sine of theta. And that is the proof. Very short, right? Cosine of pi over 2 minus theta is just equal to sine of theta. Very, very nice, clean proof. Remember, when you're evaluating trig functions at the axial or quadrantal angles, it's much easier to graph the base graphs for the sines and cosines so you can quickly read off the y values. This is a highly entertaining problem only because I know where it leads. And if you have, maybe you're watching this and you're in calculus and you're just reviewing your trig, then you also know where this leads. This is a derivative. And so, or it's part of a derivative, I should say. So anyhow, we want to prove that this is a true statement. How do you do it? Often with proofs, and this is, by the way, I think I didn't mention it when we started up, but this is part 3 of proving trig identities. Every time we get a new piece of trig technology or theory, we do yet another part in proving trig identities. So in the previous videos on proving trig identities, I mentioned kind of a tactic. And the tactic to proving trig identities starts with choose the uglier side. This is an exception to that rule. I would probably not start with the uglier side here. By the way, if you don't know all those, go ahead and watch one of my previous videos. But for now, I'm just going to say the uglier side obviously is the right-hand side. But that's not going to lead us anywhere. That's just going to be a big fat mess. So I highly recommend, in this case, starting with the left-hand side. If you didn't know that, which I don't blame you, you would start on the right-hand side and you would get stuck. You would eventually not be able to do anything. You just wouldn't know where to go. And in that tactic in the previous videos, I mentioned if you get stuck, go to the other side of the equation and work on that side for a bit. And that's exactly what I'm going to do. I'm going to just state right now, if you start on this side, you will get stuck. So instead, I'm starting on the left-hand side. I'm saving us the headache. So the left-hand side, well, that's the sine of x plus h minus the sine of x. And that's all being divided by h. There's not much I could do with that, except that I have the sine of a sum of angles. So at least I could use that trig identity. I can use a trig identity to simplify that statement. So we'll say it's a big old fraction bar. Sine of x plus h is the sine of x times the cosine of h, plus, because the sine keeps its sign, sine of h, cosine of x, and then we still have a minus sine of x hanging off the back end. And this is all over h. And then I also mentioned in one of those previous videos on proving trig identities, keep your eye on the prize. Take a look at where you want to end up. Notice I want to end up at two completely separate fractions. So I'm going to break this into two fractions. One that has, let's take a look at what the difference between these two fractions are. One will have sine of x with no other sine of x, and the other one will have cosine of x with no other cosine of x. So I'm going to try to start separating that numerator to be just stuff with sines of x's and stuff with just cosines of x's. So let me zoom in here. And stuff with sines of x's. Well, I have a sine of x, cosine of h. And on the back end here, I have a sine of x. So I'll just say minus sine of x. And we still have this plus. I'll write this as cosine of x, sine of h. I just swap the order because multiplication is commutative. And this is all over, this is all over h. However, we know that you can break a fraction from our arithmetic. If you have a plus b over c, we know that we can write that as a over c plus b over c. So I'm going to break this fraction into two fractions. There we go. So I have my two fractions. Notice the second fraction actually is pretty much done. It's a cosine of x times sine of h over h. So that one's done. The first fraction, I need to move these sine of x's out. So I'll factor them out. I'll factor a sine of x off that numerator. And I'm left with a cosine of h minus 1 over h. On the second fraction, I'll factor out a cosine of x off the numerator, which just leaves me with a sine of h over h. And notice, that's exactly what we wanted to prove. We wanted to prove that that left-hand side would turn into the sine of x times cosine of h minus 1 over h plus cosine of h, plus cosine of x times sine of h over h. So anyhow, that you will see again in your calculus course, because that is actually where the derivative of the sine comes from. Now, if you have questions on any of this, you can always leave comments in the comment section on any of my videos. You can always ask, because I am totally happy with responding to those comments. But for now, let's go ahead and move forward. Looking at this example. Now, picking a side to start on in this example is going to be somewhat of a challenge. The most complicated side is the right-hand side, so that's where I would probably start. Again, this one, I'm not going to just tell you, oh, one side won't work. I'll just go ahead and start it like this. I'll say the right-hand side is the cosine of A minus B over cosine squared of A minus sine squared of B. Now, I have a trig identity I can use right now, and that's the difference of angles formula for the cosine. That is going to be, in the numerator, a cosine of A times a cosine of B plus the sine of A times the sine of B. And this is all over the cosine squared of A minus the sine squared of B. Now, taking a look at this, I would honestly stop and just go, I don't even know. Like, I don't know how this is going to reduce down to become that secant of A plus B. I would probably pause on this. So I'll hit the pause button there, and I would go over to the left-hand side. There's nothing wrong with that. What you don't want to do is you don't want to multiply between the sides. So I don't want to move this to the other side or something like that. That's completely illegal. Moving between sides during a proof implies you're assuming the two sides are equal. You don't want to do that. But when I say moving, I mean moving terms between sides. But you're totally allowed to pause on one side while you're working and then start up on the other side and work on the other side a little bit. That's totally okay. So I'm going to go to the left-hand side here, and I'm going to say, well, let's see what that turns into, the secant of A plus B. Well, I know by the reciprocal identities, that's just 1 over the cosine of A plus B. And I now know the cosine of A plus B is just going to be 1 over the cosine of A, cosine of B, minus, because again, the cosine doesn't like its sine, so minus the sine of A, sine of B. Now you take a look at this. These two sides do not look equivalent at all. Not at all. And this can be disconcerting. This is actually really kind of a challenging proof, I think. But it turns out that you can force things. Like, this is what my tactic would be. I'd look at these and say, man, I just don't know where to go from here. Well, look at the differences between them. For example, the numerator in this right-hand side is cosine A, cosine B plus sine A, sine B. And notice this one doesn't have that. But you know what you can do? You can multiply numerator and denominator by cosine A, cosine B plus sine A, sine B to force that numerator to look like the numerator on the right-hand side. So let's go ahead and multiply top and bottom. This is like, usually for me, a last-ditch effort. For me, I'm like, if I just don't know what to do, I'm going to start forcing things a little bit. I want that numerator, their numerators to match. So I'm going to multiply top and bottom of this fraction on the right-hand side by cosine A, cosine B plus sine A, sine B. So let me do that. Cosine A, cosine B, really good problem actually, plus sine A, sine B. By the way, this should let you know, I do not try these problems prior. I just write them down. I think they look cool, so I'll write them down and then I do them in my lecture video. So you'll see me and hear me actually kind of think while I go through these problems. I'm not doing these, from rote memory. Oh, I've done this 15 years. I've done this problem over and over and over. Nope, I've never done this problem. But it's a really cool looking problem. Let's see. Multiplying through the numerator is going to be cosine of A, cosine of B, and then what is it? Plus sine of A, sine of B. The denominator is really cool. You might not think so, but I do, because the denominator is cool because of the simple fact that this picture right here, I'll call happy face. That picture is the same as this picture. Happy face. This picture right here, I'll call star. If I can remember how to do a star. It's been since elementary school. There we go. Is the same as that picture right there, star. So notice it's happy face minus star times happy face plus star. That's called a difference of squares. So it's going to be happy face squared minus star squared. That's what the multiplication will be. So let's go ahead and write that down. That's going to be the first thing squared minus the last thing squared. That is, it's going to be a cosine squared of a cosine squared of b, and then minus a sine squared of a sine squared of b. Okay, so that gets us that far. Now, where do I want to end up? Oh man, I want this to end up with a cosine squared of a minus a sine squared of b. Wow. So we're still not there. We're very close though, but we're not exactly there. Okay. Well, our numerators match. Let's see what else we can do. Well, notice I don't have in this denominator a cosine squared of b. We have an identity. Man, this is a really good problem. We have an identity that tells us the sine squared of b plus the cosine squared of b must equal 1. There must be a faster way to do this, but that's okay. I'm okay with this. So this means that if we had a cosine squared of b that we want to get rid of, we could trade it out for a 1 minus sine squared of b. And notice in the side we want to match here, there's no cosine squared of b. So what I'm going to do is trade out this cosine squared of b for a 1 minus sine squared of b. Wow, cool problem. So let's see, this is going to be the cosine of a, cosine b, plus sine of a, sine of b, all over. I have this cosine squared of a times the quantity 1, whoops, screen moved on me, 1 minus the sine squared of b. So let's just see, minus, and now I'm going to look over here and let's see what that other term has. We don't have a sine squared of a over here, so I'm going to do the same thing. I'm going to get rid of the sine squared of a by noting that the sine squared of a plus cosine squared of a is equal to 1. Therefore, that sine squared of a could be traded out for a 1 minus cosine squared of a. So that's what I'm going to do. I'm going to trade out that sine squared of a. Let me use a different highlighter here. Let me make sure I click it. That sine squared of a, I'm going to trade it out for a 1 minus cosine squared of a. So it's a minus quantity 1 minus cosine squared of a. And again, the reason why I'm doing that is because I don't have a sine squared of a in that other fraction that I want this to eventually look like. I want these two fractions, this guy right here where I paused, and this fraction that I'm working on, I want them to be the same. We're so close now, because now if you simplify this, you'll get the cosine of a, cosine of b, plus sine of a, sine of b, that's the numerator of the other fraction, so we're okay there, is being divided by, now I'm going to distribute, this will be cosine squared of a minus cosine squared of a sine squared of b. Let's see, minus 1 times a sine squared of b, minus sine squared of b, and a minus 1 times a negative or plus cosine squared of a sine squared of b. Notice the negative cosine squared of a sine squared of b cancels with the positive, and we get our answer. This is equal to cosine of a, cosine of b, plus sine of a, sine of b, all over cosine squared of a minus sine squared of b, which is actually where we paused, right? That's equal to the pause. That's how I would write it, because we went down to this point right here where we paused and we just said, well, I don't know what to do with that. And you could see why. It's a lot of work. So this is a great example to showcase that when you're doing trig proofs, often you're just going to run around a little bit And that's totally fine. There's nothing wrong with that. It's what is wrong is to not try. And what is wrong is to just give up early. Don't do that. You want to be, I mean, if you're taking a trig course, it's because you're going into STEM. And if you're going into STEM, you're going to need to be able to think critically and take your time with your thinking. I'm not saying that everybody would be able to get this problem right from the get-go, but I am saying that you have the ability to, and just give yourself the opportunity to pursue that ability. Anyhow, all right, we're done with this video. I will see you in a future video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.